Hello, this is Nathan Law, and today I'm doing my presentation about RSA cybersecurity, and it is about how science and math sustain global e-commerce by protecting our personal and personal information. Yes. Okay, looks like my old computer doesn't want to work. Let's see what I can do here. There we go. Now the space we're going to work. All right. So, overview of this presentation. So we're going to go over the RSA's background and the importance of RSA in our day-to-day lives. We're going to go over how it works, and then we are also going to talk about future implications of cybersecurity. So here, for a starter problem, just to kind of get your mind going about how this stuff works, here's a problem. In 30 seconds or less, what is the prime factorization of 2,491? Feel free to pause or now. I'm just going to move on so that the presentation doesn't take as long. It is 47 times 53. Now, I'm assuming, like most people, you didn't get that. I didn't get it. This would have taken me like 30 minutes to figure out, right? So this basic problem, which is very difficult, is the basis of cybersecurity and online transactions. And this problem is incredibly easier than what you're going to see in actual RSA encryptions. So RSA cybersecurity was developed in 1977 by MIT professors Ron Rivest, Adi Shamir, and Leonard Ottoman. And this is why it's called RSA, their last named initials. And what it uses is a one-way function which encrypts information and it creates personal keys for each user while maintaining one public key to make sure that transactions are easy. Now here's a little aside on one-way functions because they're really important to how this works. So any function is inherently two-way, like addition, subtraction. You can do something plus 2, something minus 2. That's two-way. Or same idea with multiplication, division, or taking exponential or logarithm, etc. And each function essentially undoes the others. So in that sense, some are easier than others. Thinking about when you learn how to add, you don't like when you learn how to do basic arithmetic, you start with addition because it's easier. So in a way, prime factorization is similar because multiplying two things together to find the number is easy, but taking that number and finding two numbers that multiply to get to it is hard. And so for this reason, it's used in encryption. So cybersecurity is extremely important because our economy relies heavily on global e-commerce, especially in these times with the coronavirus. And the companies like Amazon, which are so important to us, would not exist. RSA protects our financial, personal information, and this is super important because no one would buy stuff online or use online services if their information wasn't protected. So how it works. Each person has a unique number, which we can represent as C to the E modulo N, that encrypts their information. I will come back to that notation in a moment. And what this does is allows them to purchase goods over the internet, and their C, the E, is public. That's not a secret, but C is not. C is your credit card number. That's only you know that, hopefully. And what this number that you have is part of each vendor's database, and the company, using properties of the factoring and basically shuffling the numbers, and knows how to find each person's specific number using clock calculators. Here's an aside on clock calculators. Well, clock calculators, it works like an ordinary clock. So if you think about like if it's 10 now, what time is going to be 16 hours? It's not going to be 26. It's not a time. So what we do is we subtract 12s off of it until we get a number that's less than 12. And so that's 2 o'clock. And what this does is allow us to write large numbers in much shorter notation. And here we're getting back to the notation. So based on this above calculation, 26 modulo 12 equals 2 because there's 12 hours on a clock face. So the numbers in the parentheses can be any integer greater than 0. So back to how it works. Each domain, each vendor, they use a different size clock calculator to find each user's number. Now, these are not anything like a clock that you put on your wall. This clock has up to 600 digits. Not all of them do, but the biggest ones do. And for some perspective, there's 10 to the 80th power atoms in the known universe. So we're talking 1 followed by 80 zeros. We're talking about a number that is over 500 digits longer. So, and this number n is factorable into 2 primes, p and q, which are both very large and they're secret. So this is back to the challenge problem from earlier. So what the companies does is they have their person's info, their number, the C to the E modulo N. It's like a playing card in a just massive deck, and only the company knows how many times to shuffle this deck in order to get your information to the top of the quote-unquote deck. So they use discoveries made by Pierre de Fermat, who was on the top right, and Carl Friedrich Gauss, who's on the bottom right. There's a special number represented by D, which tells the company how many times to shuffle the deck, and D is a secret. And D will explain how D is found later using prime factorization. So after shuffling the card D times, the person's info magically appears, keeping your info safe. So shuffling the deck, think about it this way. In a standard 52 card deck, 8 perfect shuffles are needed to bring the cards back to where they started. So therefore D equals 8. So people's information is like these cards that will reappear when shuffled correctly. So finding D. D is not random. It's related to P and Q, the prime factorization of N, the large number that is the size of the clock calculator. So D is equal to the quantity P minus 1 times the quantity Q minus 1 plus 1. And with this formula was discovered by Euler, who pictured on the right, who took what Fermat discovered and just took it a little bit farther as a generalization. So hackers can't find P and Q because N is just insanely large, and the companies change N every few months, so it's basically impossible. So users' personal info stays safe and secret, and people feel confident buying things online and having their information online. So the impact of all this, RSA is the best encryption method we have so far, but it is threatened because of its difficulty in hacking is based on our lack of understanding of prime numbers and how they're distributed throughout the numbers, basically. There's a lot of number theory that goes on there, and part of the big part of number theory right now is the Riemann hypothesis. There's a lot of people trying to prove it, because what it does is it basically says that prime numbers do have a reason to where they're spaced out. It's not random. So if this is proved, this would become a problem, because people would be able to find factorization of N and find P and Q, which then they wouldn't know how many times it's shuffled, and then they'd be able to get your information. So this would be a problem, and this leads to a difficult decision where you're choosing between keeping everyone's info safe and everyone can buy stuff online, and then you're also looking at, well, if I don't do that, then we're leaving out finding mathematical truth, and it could have great applications otherwhere, like other places in science and math. So it's an interesting conundrum that they're facing. And my works cited, the end. And I hope you enjoyed my presentation on RSA cybersecurity.